Good afternoon, fellow AAE 590 students. Good morning, rather, to those of you that are watching in class. I always forget that this class actually airs at 9:30 in the morning or whatever it is. Today I'm going to be talking about NASA's new heavy launch system, the Space Launch System. There seemed to be a good bit of interest after Boeing CEO Dennis Muilenburg was up on campus a couple weeks ago, and I have some firsthand experience with it, so I thought I would share. NASA announced the Space Launch System program on September 14th, 2011. It's designed to provide a safe, affordable, and sustainable means of reaching beyond our current limits, basically farther out into the solar system. It was designed in partner with Lockheed's Orion Multi-Purpose Crew Vehicle, though it does have a cargo configuration as well. And it's NASA's first exploration class vehicle since Saturn V. And one of the goals of the program was to leverage technologies used in both the Space Shuttle and Constellation programs. And it was kind of to follow in the footsteps of the Saturn V, if you will. The program's based out of Marshall Space Flight Center in Huntsville. Assembly is done at Michoud Assembly Facility in New Orleans. Hot fire and green run testing is done at Stennis Space Center in Mississippi. Structural testing is done back at Marshall, and final assembly and integration is done at Kennedy. That picture down at the bottom right is the liquid hydrogen tank under construction at Michoud. The base specifications for SLS are generally referred to as Block 1. Like I said on the last slide, they utilized a lot of technologies from Space Shuttle. The RS-25 engines, the four main liquid hydrogen, liquid oxygen engines, are all from the Space Shuttle. They put out a sea level thrust of 418,000 pounds and a specific impulse of 366 seconds. The two solid rocket boosters are also Space Shuttle derivatives. They're a little bit bigger, but the design is still the same. They put out 3.6 million pounds of thrust, and each burns for just a little over 2 minutes. The upper stage on Block 1 is known as the interim cryogenic propulsion stage. It's a modification of the Delta cryogenic second stage, which goes on the Delta IV Heavy, launched by United Launch Alliance. It has a single RL-10B engine, which provides 24,750 pounds of vacuum thrust and a specific impulse of 465.5 seconds. The Block 1 configuration has an initial lift capacity of 70 metric tons to low Earth orbit. The four liquid hydrogen, liquid oxygen engines plus the two solid rocket boosters provide a total of 8.4 million pounds of thrust. The initial launch, otherwise known as Exploration Mission 1, was planned for late 2017, with the first crewed flight, Exploration Mission 2, scheduled to follow in mid-2021. SLS is known as an Evolved Expendable Launch Vehicle because it is designed to progress from one block design to the next. Block 1B is designed to incorporate the Exploration Upper Stage, which is an upper stage that Boeing's developing on a clean slate design. It uses four RL-10C engines, each providing 22,890 pounds of vacuum thrust and a specific impulse of 449.7 seconds. Block 2 is designed to use advanced solid rocket boosters, as well as the Exploration Upper Stage. Those boosters are still under development, so we don't have a whole lot of specifics on them yet. But down at the bottom here, we can see a comparison of the masses to low Earth orbit, translunar injection, and heliocentric orbit. Block 1 was designed to carry 70 metric tons to low Earth orbit and 26 to translunar. Block 1B can carry 105 metric tons and 30 to low Earth orbit and 37 to translunar. And Block 2 is the heaviest, most capable version, is designed to carry 130 metric tons to low Earth orbit and 45 metric tons to heliocentric orbit. And now the current program outlook. That's what everybody is kind of interested in right now. Boeing still claims the initial launch, Exploration Mission 1, will take place in 2020, as Dennis Muilenburg stated when he was up at the Purdue campus a couple weeks ago. I believe it was last week, the forward join process took place at Michoud. That's what that picture is down at the right. Forward join is the oxygen tank, the inner tank assembly, and the forward skirt being joined together. It's one of the main structural joins that takes place in the assembly process. That's kind of where the program is right now. Last year, over the course of 4 months, the Office of Internal Guidance audited SLS as a program. They found issues with the program management, including an underestimation of the scope of work, technical and infrastructure problems, and hardware and software that is needed for testing was behind schedule. Granted, some of that was affected by Hurricane Harvey, which did come through at Stennis, and there's not really anything that anyone can do about that. But one of the takeaways from that audit was that it's expected to cost a total of $8.9 billion by the time 2021 rolls around, and that's almost twice what was originally planned for the program as a whole. One of the issues has been with the exploration upper stage designed for Block 2, or excuse me, Block 1B. The mobile launcher at Kennedy is not strong enough to support the extra weight of the stage with the exploration upper stage on it. So they had to decide whether to modify it, take it offline, or to build a whole new one. They decided to build a second mobile launcher, and that's added 3 years to the timetable for when Block 1B can launch. And then, kind of hot off the press from last week, NASA actually announced that they're looking into using commercially available launch systems for the first Orion lunar mission. They're considering both Falcon Heavy and the Delta IV Heavy because they don't believe that SLS will be fully developed by mid-2020. The only problem with that is that it would require separate launches of both the Orion vehicle and a second or an upper stage. So there would have to be some on-orbit assembly there, which obviously adds a good bit of complexity. So here I've included a snippet of some of the missions that SLS is supposed to fly. Exploration missions 1 and 2 are designed as lunar orbit or lunar flyby, both with Block 1. And you can see those are designed to launch June of 2020 and June of 2022 respectively, with Exploration Mission 2 being the first crewed mission. The Europa Clipper mission, which requires a heavy launch capability to go into Jovian orbit, scheduled to launch in 2023, also on a Block 1 vehicle. The first Block 1B launch, Exploration Mission 3, is scheduled for 2024 out to Lagrangian points. Exploration Mission 4, a similar mission, scheduled for 2025 to the Lagrangian points. And then Exploration Mission 10, which would theoretically be the first Block 2 mission, scheduled for 2029, also out to Lagrangian points. Those last three would all be crewed launches. Like I said at the beginning of the presentation, I do have some personal experience with SLS. I worked on the program for a while, so I was able to see some of the good and bad, and just a couple things that I would like to share without getting into too much detail. One of the things I did notice was that the design process seemed a bit convoluted. It was very procedural rather than relying on engineering experience, which it does have its pros, but it also tends to slow down the design process a little bit. Some of the requirements coming down from program management changed a little bit, and they were often vague at times, which makes it a lot harder for the designers. There were few senior engineers on the program. A lot of the design groups were led by mid-level, mid-career engineers, some of them kind of early to mid-career engineers, and I think that oftentimes people can get a little bit over their head in situations like that. Dr. Spencer even talked about that on one of the programs he worked on at JPL, I believe. One of the things that I noticed was that they really considered production aspects of the work kind of late in the process. When you have a really big or really complex piece of hardware, you need to consider production kind of at the beginning, because designing or building a rocket, something as complex and as large as a rocket, it's not easy. So you have to take into account facility requirements, tooling requirements, all that stuff, and it seemed like the program was a little behind the ball in that area. And similar to that, a lot of the work instructions were overly complicated. The technicians would be working for 12 or 15 operations before they would actually get their hands on hardware, and that's just time that's not being spent on the actual spacecraft. kind of one of the ways that I like to sum it up was that there were too many hands in the cookie jar. Everybody wanted a little piece of it. Everybody wanted their opinion to matter in every circumstance. So things just got bogged down. And I wish I could take questions from you guys just to kind of hear what your opinion is for what's in store for SLS right now. There's rumors that NASA wants to build the Lunar Gateway, which would be a space station in orbit around the moon, and that they would need SLS to help out with that. Obviously, it's the heaviest lift vehicle we have right now, so if they do want to take a trip to Mars sometime in the near future with a large cargo, SLS would be beneficial for that. But there are also a lot of people in the space community that want the program to be canceled simply because of the huge budget and the fact that it's taking up a lot of resources that could be going to other programs that are actually making more progress. So I hope you guys enjoyed. Feel free to discuss any kind of opinions, questions that you have, and I will listen to them when the lecture gets posted online. Thank you.